you think we can make these people go?
If you click on the left, you can move that wherever you want. Yeah.
Cool, thanks. So welcome. I'm presenting today on how we've used meaning fields to understand students' mathematical drawings. This is under the umbrella of the ASKTM project, for which Eric Jacobson is one of the PIs, funded by the NSF. The ASKTM project involves large data sets with a relatively complex survey design, and its goals are related to mathematical knowledge for teaching. This study is just drawing on pilot data for that larger study. It's much smaller, qualitative in nature, and somewhat theoretical in purpose. But if I use the pronoun we, I'm referring to work that was done within the context of the larger project. So particularly, we're going to be talking about spatial representations of quantity, flexibility, and a little bit about data sources as the introduction. Spatial representations of quantity, in terms of this presentation, I'm just going to call them representations. So if I say representations, I'm referring specifically to things on the left. Things on the right are representations of quantity, but they're not spatial in nature. A little bit about flexibility. Flexible use of representations is explicitly encouraged in pre-service teacher textbooks like Van de Waal's Teaching Developmentally, which most people in the room probably have picked up once or twice, maybe 100 or 200 times. But flexibility is also encouraged throughout the Common Core standards of mathematical practice and on a number of NCTM's position statements. Generally, calls for flexibility do not include caveats that might suggest there is a cognitive cost for students when teachers use representations flexibly. That is, teachers might use representations flexibly in class out of necessity because there are just a limited number of viable representations. Because flexibility can elucidate underlying base 10 structures, for instance, or other constructs that are mathematically important. Or because flexibility is just simply encouraged by the authoritative sources that I talked about above. Our data includes several examples where children appear to be basing incorrect conclusions on flexible use of representations, pointing to the possibility that there is a cognitive cost in terms of confusion associated with flexible use of representations.
Do you mean flexibility in a specific way that's specific to mathematics ed?
We're going to drill down into it, yeah. It's sort of undefined in these authoritative sources. Do flexibility, whatever that means. So I think one of the things we're sort of looking at is, well, if you just sort of do it without knowing what you're talking about, maybe there's some problems associated with that. Context. So we surveyed 10 teachers and their students. They were chosen as a representative sample of urban, suburban, and rural areas of Indiana. Students answered questions that included representations. The student answers that included representations are the main data source for this project, but I'm also going to bring in some interview data. The interviews were conducted at the teacher participant schools a few months after the surveys were collected. This allowed us to ask questions inspired by their students' responses. Concurrently, we developed a parallel instrument for 5th grade, in addition to the 4th grade, where the N, in terms of number of students for the 5th grade sample, was 169. So it's a slightly smaller sample for 5th grade. As a point of interest, 23% of the 4th grade student samples included representations of quantities, but only 4% of the 5th grade students use representations of quantities. So there is a precipitous decline in terms of the frequency of use of representations as a problem-solving tool from 4th grade to 5th grade, at least in our data set. which should maybe set off alarm bells in the sense that a critical tool is being underutilized. But also there's a caveat here that the instruments weren't identical. So it's possible that the 5th grade items just didn't require representation use. So they didn't use representations, but that seems like maybe there's something more interesting happening.
So just quickly, you're just referring to spatial representations.
Right.
Yeah, so I actually think including spatial will help.
Okay.
when you say that.
And were these classes all in the same district, or were they a variety of different places?
It should be representative of Indiana at
Oh,
large,
okay.
so
All right.
urban, suburban, and rural.
So it's not something going on in the school that's causing this.
Right. So yeah, we hope that there's something more interesting than just that the problems were easier for 5th grade students, so they didn't use representations. So what's going on with this? This is a student response to the question, write 2 fractions that are equivalent to 3/4. All of our questions ask students to use pictures, words, or symbols to explain. So as I was coding like 1,700 student work samples with the other ASKTM graduate students, I ran into a bunch of things like this, where I was just sort of like, I don't know exactly what's going on with this work. Some of them were easier to interpret. Okay, so we use meaning fields to try to interpret students' drawings, which is grounded in part in Phil Karspecken's work, but also sort of inspired by Susan Wright's use of arts-based educational research. We're going to discuss meaning fields more fully momentarily, but Susan Wright analyzes the artistic drawings of kids, and her conclusions suggest that children's artwork can represent sophisticated ideas, but in ways that are opaque to the researcher. So here's one of her images that one of the images that she analyzes. It appears to maybe be 4 dogs and 2 floating people, but the child intimated that it's actually supposed to be sort of like keyframes in an animation. This is a police dog in training, sliding over a slide. So, you know, I think we probably could have guessed that, but even some that are much more challenging to interpret are sort of subjected to this analysis. So I was sort of hoping that when confronted with a bunch of examples that were confusing to me, I'd be able to kind of parse the intended meaning that the students had for their drawings, and maybe they would follow an internal logic that I couldn't see immediately, but that would be clearer upon analysis. To do that, we used meaning fields. So meaning fields are an integral component of Karspecken's pragmatics, which is based on Habermas's theory of communicative action. They're used by researchers to identify the range of possible interpretations of a communicative act. The structure is horizontal, meaning the field never captures every possible meaning, just the sensible ones based on context. Nevertheless, it's useful to write down these possible interpretations because, as Karspecken says, you cannot know for certain what an actor intended with her act. You cannot know for certain what impressions of meaning were received by those witnessing the act or directly addressed by the act, but you can specify possibilities. A meaning field is such a range of possibilities. And then one thing that makes meaning fields unique from my perspective is the use of logical connectors between the different possible meanings. So meaning fields are utilized by researchers to enumerate the possible meanings of a speech act. So a researcher might record a conversation where a participant says something like, "We should grab a coffee." The researcher, if uncertain about the intended meaning of the speech act, might create a meaning field where some of the possible interpretations are listed out with logical connectors. So that looks like maybe I'm sleepy and need a little pick-me-up, or I like you and would like to spend more time with you, and or I'm worried about your progress on your dissertation, but I don't want to appear threatening. Not saying which one of those are based on personal experience. So cognitive load is sort of an unrefined idea here that I'm presenting, but there's a potential connection between how well populated a meaning field is and the cognitive load associated with interpreting the speech act. So because any statement with more than one element in the meaning field is ambiguous, the actors have to weigh which one is more likely. So the larger the meaning field, the greater the ambiguity, and consequently, the greater the demand on working memory, which is sort of one definition of cognitive load.
And whose working memory are we talking about here?
The person hearing the speech act. So in this, in the broader context here, sort of imagining a fourth grade student sitting in a classroom hearing their teacher talk, potential meanings that they have. If the teacher is ambiguous with something, there are going to be a lot more potential meanings than if the speech act is disambiguated. So if somebody says duck, the meaning field could be, I should quickly reduce my vertical extension because something is going to bonk me on the head if I don't. Or look at that waterfowl. Right? If the person to whom duck is directed cannot immediately discern the intended meaning, they must disambiguate the speech act, which takes work. We might then conclude that an ambiguous statement would have more elements in its meaning field than a disambiguated counterpart. Which means that the cognitive load associated with interpreting a speech act should be positively correlated with the number of elements in the meaning field. Again, this is a rather tentative connection. Meaning fields and cognitive load developed from like totally different meta theories, but they sort of seem like they chime a little bit. So I think maybe it would be worth working that out a little closer. Before we can make meaning fields of student representations, we have to take a closer look at the logical connectives that are deployed in meaning field analysis. So these are just the truth tables for OR and XOR, but researchers use and, or in meaning fields. But as will become clear momentarily, it's important for the purposes of this study to define the OR operator as the inclusive or logical disjunctive. This is the meaning that most of us as STEM folks probably are familiar with, but it's pretty uncomfortable for non-STEM folks. Essentially, the inclusive definition of OR allows for both proposition connected by the operator to be true. So a mathematician who says, I'll take my coffee with cream or sugar would be happy to have coffee with just cream, happy to have coffee with just sugar, or happy to have coffee with both cream and sugar. Which is, again, a little bit weird, but if symbolic logic was central in your formal education, you're probably used to that. To non-specialists, the more comfortable interpretation of the disjunctive is the exclusive interpretation, often denoted as XOR. The computer scientist who says, I'll take my coffee with cream, XOR sugar, would be miffed to find both cream and sugar in their cup. For this operator to hold the statement A XOR B, A could be true, B could be true, but they can't both be true at the same time. So for now on, I'm going to try to be careful about using the word or capitalized to mean the inclusive disjunction, and XOR capitalized up there to mean, XOR means the inclusive and OR means the, I keep saying that wrong. I'm gonna practice that. XOR, exclusive, or inclusive. Okay.
It's clear enough from the table.
Yeah.
Yeah, we'll just look at that.
But the good news is we don't have to be fussy about the and operator. It just sort of functions how you'd expect. So a quick think, pair, share. How do you think children tend to interpret a statement like you may have pizza or ice cream? So that's where you think and then talk to your neighbor and then share out.
You just think ice cream.
The context does have something to
Pizza
do
or
with
ice cream. They have a choice.
Yeah.
They have a choice. They can have one or the other.
One or the other.
And the answer's like, I'm not gonna tell.
Yeah.
it. Just ask the question, can I have both? Yeah.
So I'm hearing mumblings, but what do folks think?
We said one or the other.
One or the other?
But they'll probably ask if they can have both.
Probably ask if they can have both, yes.
Which in some ways probably adds more definition, right? They're trying to get like further definition on that thing.
Yes, that's a very good point, and speaks to a slide I deleted. But maybe we'll get to it at the end if necessary. But we don't actually have to guess. For young children, yeah, so anyway, I imagine most of you said that you interpret it like you interpret it, right? It's a exclusive definition of or. If you told your kid that they could have pizza or ice cream and they came back with both, you might be upset with them. But we don't have to rely on just an informal poll. There's findings in cognitive linguistics that suggest that actually young children interpret disjunction as inclusive. There are some limitations to applying this finding to our results because the kids that they used in their study were younger than ours. They were 5 and 6 years old. But that being said, it seems possible that developmental delays might occur for some students where this acquisition of disjunction is delayed for some reason, or educational background, or just like being in a complicated and confusing context like a math classroom. It seems possible that that interpretation of or being exclusive is not automatic for some kids. Okay, so back to meaning fields for a second. This is just a cropped portion of a student work sample, but you can see a 10 by 10 grid. Looks like 60 of the squares are filled in and 40 are vacant. The first element in the meaning field might therefore be 60 holes, right? It could be 60 holes. But like most math educators here are probably aware, it's really common to encourage this exact same representation of 6/10, 60 parts out of 100. So the first pass of this for math educators would probably be, this could be 60 XOR 6/10, right? Is that sort of, okay. Here's the whole image. And as you can see, the child is represented 6/10 and 60 as equivalent. And when asked to order the quantity, the kid thinks it's clear that 6/100 was the smallest, but since 6/10 and 60 looked the same, the child decided that 6/10 was larger than 60. Or perhaps the and up here in the corner, I should have clarified. This is the answer, right? They're saying 6/100, 60, and 6/10 are ordered quantities there. So the and there is a little ambiguous. The child could be saying that 6/100 is the smallest, and then these two quantities come together and are equivalent, but larger than 6/100. Regardless, it's problematic that the kid is not distinguishing between those two representations, right? Using the same representation to mean two different things at exactly the same time. Yeah, we can conclude from this the child doesn't have any serious compunctions about allowing one representation to mean two different things at the same time. So if they were saying that the original grid for the child would have a meaning field of 60 or 6/10 in an inclusive sense, right? They're letting both of them into the party there. So if we have some hypothesized trajectory development here, a teacher who says that this grid can be used to represent either 60 or 6/10 might actually make the interpretation of that more ambiguous, not less, right? Okay, so to talk about these special types of things, we introduced the term hybridization. So in our context, hybridization is a term specifically for spatial representations that include the conjunction A and B that children might understand as a possible meaning of A or B, depending upon their point in the developmental trajectory. So the hundreds grid that the student was using to represent 6/10 and 60 is a hybridized representation simply by virtue of the fact that the kid can mean two different things at the same time. So perhaps more illustrative, here's another example of a hybridized representation. The student, this is in response to write the fractions 2/3, 3/4, and 3/8 in order from smallest to largest. And we see that the child has drawn several circles, presumably to draw set models of the three quantities, filling in 3 circles out of 8 to represent 3/8. Things get hybridized though when the kid partitions those circles. And I could imagine somebody saying, well, those are just peace signs, that they're not partitioned circles. So we head you off at the pass. We can see here that these are really representations of 2/3. That's sort of what the kid is getting at here. It's unclear why these are all partitioned into thirds, but they're using these things to be both at the same time. And
it's consistently not a third, right? Like they're drawn consistently, but they're actually not. Like we all interpret it as thirds, but that's not the way it's drawn actually, right? In other words, the pieces of the pie are basically like 40%, 40%, and then 20%.
yes.
It's sort of drawn.
Yeah, they're not, it's not clear. I mean, the kid wasn't being careful in their partitioning.
Right. That's what I mean. It's sort of interesting, but we automatically, I think, automatically go to like, that was a pie cut into 3 pieces.
Yeah. And I think that was the intention of the kid. It was to partition them into thirds, that they just sort of were being kind of sloppy because they're doing that partitioning to a whole bunch of objects, right? You really only need to partition 1 circle into 8 pieces to represent 3/8 with an area model or a circle model. But they're doing that here 8 times. So there's something going on here. So yeah, this is both types of representation. It's a set model and an area model mixed together in a way that's maybe not viable, right? It doesn't actually, like the 2/3, for instance, on the far right doesn't really, like, this is 2/3 and this is 2/3, but this is not exactly.
2/3 of 2.
Yeah.
It would be interesting to know the order that the child drew them. Because one could imagine that he or she started with 1 and then was trying to figure out some way to come up with common units that ended up being the hybridized representation that you're seeing here. So I wonder if just trying to look at the end product is part of what makes this so hard to interpret.
Definitely, yeah. If we could sort of ask the kid what was going on, it might help too. But yeah, just to see a process. But this is all survey data, so.
That's what I was wondering. It's almost like an attempt at trying to make them equivalent fractions
Yeah,
or something
that's
like
what
So like you
that-
pick one thing to draw and then shoot, everything else needs to.
Yeah, then it doesn't work and you're trying to draw the others and you don't have enough paper or places to erase, or kids don't like to erase stuff. They just rather keep writing for the most part.
Okay, so these hybridized representations actually appeared throughout our data set on various different types of questions. But They were localized in sort of clusters in specific teachers' classrooms. So I think that suggests that it's not totally random. And so maybe that teacher or those teachers had kids that were below grade level or something, or it could be that their communicative practices could be improved to help their kids disambiguate these things. Okay, we're doing actually okay on time. So
Do you have any sense of that of how, and I guess maybe just in mathematics in general, are there certain teachers who are more likely to use visual representations as they try to explain concepts than others?
Yeah. So just in terms of fluency, we did some interviews with, I did an interview with, oh no, I didn't. You did an interview with a math coach, and their answers to the representation questions were really robust and well thought out, and they use representations all the time. I did a interview with a teacher who said, I just don't use them. I know I'm supposed to, but my kids are confused by them, so I just don't use them. So I think it's sort of, people are all over the board, but it's encouraged by these authoritative.
Yeah, right.
It's supposed to happen. But
I would imagine that it does have this trickle-down effect on, like, if they use them frequently, then probably their students are more comfortable with, in theory, in using them or trying to make explanations in using them. But
I think that's probably true even in a stronger sense. Kids probably use them in the way their teachers use them. So not just frequency, but also some
that's where, like,
qualitative things about kind of how they're used. And
going back to the pies, like, I'm trying to think of a situation where a teacher would have drawn something like that the kid is trying to, like, bring back into their working memory. And yeah, just trying to, and so I'd imagine that somebody who's using it more frequently, there's actually more opportunities for them to do some weird stuff.
Yeah.
If you only use them in a very traditional or canonical sense, or they're only seeing them in a textbook, then they're probably going to just need some more typical representations or something.
I think that's probably, there probably is some truth in that. That makes sense. Okay, so here's just an example of a child who was not incorrect in the way that they ordered their quantities, and yet still used sort of equivalent representations, right? This isn't actually 6/10. It looks like it may be 2/10 or something, but I think it's sort of just a sloppy drawing. Here's another kid that put 60 in the middle again in equivalent representations. And these were by no means were these like a common occurrence or like a statistically significant portion of our sample. These are just some weird things I saw, right? That did happen regularly, but not like all the time.
Is that a common difficulty kids have, though, like in mathematics at about this developmental level, is ordering numbers like that, though?
Yes,
Is that a pretty common issue?
I think it's grade appropriate a question.
Yeah, so ordering multi-digit numbers and decimals in particular is challenging. There's all kinds of misconceptions that have to do with overgeneralization of whole number knowledge. So, for example, these in particular maybe aren't great, but if you had 6 for this, but if you had 6/10 and 600s, kids might say, oh, they're equal because they both have a 6. Or if you had 6/10 and then 60/100ths, like with an extra 0, they might say the 60 is more because it's like a longer number. So there's various things like this. There's less literature that we're aware of that looks at, so that speaks to kind of an ambiguity in the symbolic representation. There's less that we know about ambiguity with respect to other kinds of representations, particularly spatial representations.
here's that first example where, again, I think that those circles on the right, the question was about 3/4, and I think that they are trying to represent 3/4 with the circle diagram, but also maybe a set diagram. I think
Those last ones seem like they might have 3/4
A
shaded.
hybrid sort of thing.
Yeah,
right?
right.
Another sort of child here representing 3/4 as a pie that's being cut into 3 pieces, and then also as a set model. And then here they're using a rectangular model, but also a set model, right? 4, 6, they've got 4 of the squares shaded in and 2 unshaded. So they concluded that was 14/16. I'm not, I don't know what logic they were using there, but.
Is it all right to ask another question? I don't want to derail your presentation. Sorry, but we've done some work on data visualizations, and Michael's group has too. Is there generally a thought in mathematics education or amongst you guys that that sort of thing would be that you as an educator could sort of better understand a misconception that the student has, or that you could sort of remediate their understanding better if they've drawn these sorts of things out for you? And there you could see like, oh, clearly there's something going on, that they're making these 4 pies into thirds.
Yeah.
Or is that not a thing that like the actual drawing helps in you figuring out what their thinking might be?
I don't want to give away the goose exactly, but I think that maybe my sort of guess is that in 4th grade, we're seeing a lot of these sorts of things, and they're sort of being stamped out by their teachers. Like, no, that's not the right thing to do. No, that's not the right thing to do. Don't do that, right? And then in 5th grade, we don't see any of them. So I think, I think that they're sort of going underground, which I don't think does anybody any good. I think it's probably better to have them.
Yeah, they may just still be hampering mental representations, right? That they're like still happening, but not on the paper.
Right, and so there might be like kind of a large constellation of misconceptions that are just like totally invisible to us because they're not being represented anymore.
Do you have examples of what their textbooks were representing? In other words, what were they being modeled? And it could be that they've been shown a variety of these things all at once, and they don't really know how to use them properly. And so that's obviously happening. But I would imagine that there could be some disambiguation that can happen potentially with the material that they're being presented.
Absolutely, yes. So the business with the hundreds grid is like explicitly taught.
Yeah.
I know it's in Vanderwall, and I was speaking with a friend who's a 4th grade teacher last night, practicing my little presentation, and she said, "Yeah, that's how we teach it. We teach them that you'd represent 6/10 like this, and you'd represent 60 like this." And then when I'll get to this slide in a second, but I interviewed a 4th grade teacher, and she was answering this question, and I was asking her, "Well, do you ever have any kids that might get confused about, whether the 60 and the 6/10 are equal to each other?" And she said something like, "No, my students know automatically that 60 is the largest." And so she didn't have to represent the 60 in her mind because that was so easy and so clear and so obvious. We don't have to worry about that. We just have to worry about the decimals. That's the real problem. So I think that yes, there probably is some side-by-side stuff happening in a textbook or something, but I'm not sure.
And I wonder about what the teachers are doing also, because I'm thinking about some of Joanne Lobato's work where she talked about the focusing phenomena and the way she was looking at slope and the different ways the teachers are talking about it. And I don't remember all the details, but given that you said it looks like there's really big differences across teachers, that might be something to think about too, in terms of, are there ways of doing these that are more and less productive?
Who's this color?
Joanne Lobato at San Diego.
Yeah, I know that paper.
Okay.
I can send
Yeah,
it
let's
to you.
pick-
Cool, thanks, Eric.
I edited that paper a while ago.
Yeah.
It's been a couple years.
Here's another example of a similar phenomenon.
Yeah, so maybe to your question, in the teacher education, we talk about using these different models and kind of say, you know, there's different ways to visualize these things, and it's good for kids to have access to lots of coordinated ways of thinking about things. And the textbooks similarly present a lot of different models. And I think the textbook authors are quite good. I haven't seen, so these kinds of things aren't coming from textbooks directly, right? And there's a lot of talk in textbooks about being really clear, you know, what's the whole when you're representing fractions, and it's something we emphasize in our courses. But it's also quite plausible to me that setting up the representations and comparing between representations isn't happening. So it's like on Wednesday we do this, and on Thursday we do this, and kids are free to make connections however they may. And that's some of what we're seeing here.
Yeah, and it looks, I mean, to me, like some of the hybrid models, it looks like they're a mixture of sort of the counting, sort of like 1, 2, 3, you know, and then at the same time doing a division of it. And it's because they haven't been told that the counted model can actually be a representation of, and vice versa, and then explaining the two and how they're used over a set of classes could be a really good way to treat sort of the problems that we're seeing here. Or at least test it.
Yeah, I imagine that this could be, the teachers could speak to these issues, and probably are, right, on an individual level.
Well, and we see some classrooms in the data set where there's a lot of representation use, where these kinds of hybrid models are quite rare, and other classrooms where there's a lot of representation use and these hybridizations are kind of clustered. So that speaks to, even in our data, evidence that there's probably different instructional things going on.
Yeah. I assume everything, the kids, they aren't just putting random stuff up there. They're putting something that makes sense to them, even if it doesn't make sense for this situation. Yeah.
And that's a really important, that maybe gets back to your question, Adam, is the representation a model of thinking? And I think the risk we always make is, or a risk that's there from kind of the observer or even the teacher perspective, is to attribute meanings that, you know, the kid may or may not have. Just like with the police training dog, right? There's actually one dog at 4 different time points. It's not 4 dogs, obviously. Obviously. And so I think that's, I think it's right that they're probably representing something they're thinking, but that the teacher knows or the researcher knows what that is, you know, I think there's a tension there.
Well, so to me, yeah, I mean, to me, because we've done some of this with college kids, college students, answering some questions about visual representations. And to me, the drawings are the why, that if you're a teacher and you ask the why, right, you actually really get to see whether they sort of understand it or not, whereas they might just give you the right answer numerically. And so in that, and I sort of get the sense that it's in here too, like when you ask the why, that's when the wheels fall off. And you start hearing like, oh, really? That's why you drew it that way, or that's why you picked that graph, or they had no idea why. And so in some of these, even if they got the right ordering from the drawings, you get a lot more detail shaded in there and you go, oh, like, it's really weird. They actually got it right, but somehow they've made sense of this sort of mess of things. And so it seems like it would be a really rich place to then go back in and try to ask them for explanation or talk through their solution or something like that and see, because it seems like the schema that they're building, some of them might be pretty haywire, but if you could try to clean that up a little bit, maybe it actually has pretty positive long-term impacts. I don't, that's an ideal, like in an ideal world where you could do that with every kid, but sorry.
No, don't be.
No,
That's
I'm
great.
just taking up a lot of
so we sort of came up with 2 research questions. To what extent are students using math drawings to answer open response tasks? And what are the meeting fields for the student-generated math drawings? And to answer the first question, despite broad encouragements, like in the standards or textbooks and on the instrument itself, we found relatively few students actually making these diagrams. In the interviews, most teachers were enthusiastic about representations, but one teacher did say, I don't teach with pictures unless they absolutely need it. To answer the second question, students were asked to write numbers like 6/10, 60, and 6/100 from smallest to largest. Of the students who used diagrams, 18 correctly ordered the numbers and 12 did not. Of those 12 students who did not correctly order the set of numbers, 3 were from the same classroom, and their responses evidenced the same misconception where it's this hybridized model.
So these aren't necessarily correct diagrams. That just meant they draw to a picture. So in other words, they do, is there a, oh, right, okay, I see the last point there. Yeah, but I mean, the ones who correctly ordered the numbers, did they normally have the representation diagrams that were actually valid?
Well, I think there was one here.
Yeah, where, yeah, you had one up there where it was
Sort of like, I mean.
Yeah, that the order is right,
order's
but the
correct, but the
diagrams are
diagrams way off.
less than ideal.
Yeah.
Okay. So that would have been considered a correct one.
Yes. Yeah, we looked at the answer and said, yeah, that's right. But
Okay.
also tagged it as something to maybe come back to. So yeah, these were localized. One teacher drew the similar representation per 6/10, but didn't draw 60 holes, saying we would take the 60 out of it because the 4th graders know, boom, that's a whole number. That's the biggest number, which I think is a little problematic. Right? Implications. So we found only 23% of the student responses in 4th grade included mathematical drawings, although all 8 problems asked students to. And it seems like meaning field analysis might help unpack why that's happening.
Do you have any data on when we look 30 years back, if you ask kids to use drawings, would it be any different?
You know, I actually don't know with math drawings, but I do know that that has been a long-standing area of interest for art education. That generally student artwork drops off around, I think, 5th grade. So there's something going on there that may be totally parallel, you know, it's related.
I think it might do with skill development in preteens. I mean, you think about what is going on developmentally, you'll have people getting really obsessive about things that they can do well and getting really, so the students that are really good at art and have gotten encouragement potentially are focusing in on that, and the rest are moving on to other sort of behaviors and activities.
Makes
That's
sense.
my general initial.
Yeah, I also wonder, I feel like this came up something similar in one of the prior presentations around your work, was like almost this notion that that's childish. We don't do that anymore. We move on to more formal mathematics or something like that. And which is interesting because then I think in high school there's some bringing it back in terms of graphing, and at least in science it would be like, no, let's draw out these things. But if there's this lull, you know, it makes me wonder if it's because that in some places, right, can be the transition from sort of elementary to lower secondary or something like that. And so if there's this just sort of mindset difference amongst the teachers of like, that was a crutch we used when you were little kids, we're going to use the numbers now, you know.
Yeah, sure. The symbolic focus.
Yeah, I'd also, interesting from my mind, thinking of it from a social psychological perspective in terms of, I mean, first graders, they'll do anything because they don't care what anybody else thinks. Somewhere between second and third grade, they're starting to learn that I got to do it this way because everybody else is doing that. And that tends to make them much less likely to volunteer stuff. So there could be some of that going on too.
Right, and sort of an inability to conform because you don't know what to conform to.
Yeah, you don't understand.
And one of the things that I didn't talk about here, but that would sort of make sense is if I don't know what's going on, but I'm sitting next to somebody who does, and they're doing a representation of 6/10 and 60 as equivalent, and the teacher is saying, "Oh, good. That looks, it looks like you're doing the right stuff," and I'm doing a representation where 60 and 6/10 are equivalent, and I'm getting feedback like, no.
Sure.
It's like, well, it seems to be like it'd be very hard to tease out what the right way to use these things is in that context. Yeah. So let's see. The other thing here is that the errors were clustered in one classroom, which suggests that maybe teacher preparation programs could alert pre-service teachers to possible student meanings when representations are used flexibly side by side. A key point for teacher education is that students can have conjunctive meanings for representations. In such a meaning field, a representation might mean more than one thing in a given context. So each new meaning for a representation actually exponentially increases the number of possible meanings. For some students, representations may be linked with debilitating cognitive load because hybridization leads to a large set of potentially incompatible combinations of representations. So that's sort of trying to get a qualitative picture there of like what it feels like to be confused. Is there are all these things that can go together and we don't know how they go together.
So I guess one question, and it's always a critique I have of cognitive load theory, is that, I mean, there are some kinds of confusions or cognitive work that are really important on the way to developing robust understanding. And so I don't know that you want to say that we have to worry that we never confuse anybody. I think I'm not sure that would be what I would want to say. And it's particularly interesting, as you point out, it's in one teacher's classroom. So I think one question is to think about what are the kinds of scaffolds and support that might help with supporting productive learning trajectories in using representations, because presumably we've got good reasons for trying to use these different representations. And so it might be useful to think about, are there some of these misunderstandings that are just going off into left field and some that are actually an important part of the cognitive work that you need to do to build a more robust understanding? And I don't know, I'm just throwing that out.
Absolutely, yeah. I think that's really important, and I don't want to give the impression that I don't think flexible use is like a good idea. I think it's really important and great, but it's just maybe there's maybe this consequence of that hasn't really been explored. Okay, so also another thing is that it could be that pre-service teachers and teachers could draw meaning fields as a way to sort of structure their understanding of students' work. And may introduce pre-service teacher to some of these hybridized examples as a way to problematize the use of representations. But I think that's all. Any questions? more? Any more questions? Otherwise, I can speak to your point about the other thing along back.
Oh, right,
I've got
right,
my
right,
other
right.
slides. But, say
I
them.
mean, so in the sort of noticing realm, I'm assuming student work is a key part of that. And this would just fall into like stuff students produce, right?
Mm-hmm.
But has anyone focused on the actual sort of just looking at not necessarily just what they draw, but really the representations that they're drawing as some window into their thinking on something that you as a expert, whatever, you as a teacher, pre-service or otherwise, can, again, get something from that can help you try to figure out where to intervene and how to sort of say like, oh, okay, I see what you're trying to do there. And some of this, it almost seems like they're, one of my gut interpretations for some of this is they're over complexifying where they're like, oh, I knew they draw something. And that goes back to like the unit counting, but then, oh, they were also drawing these other representations. I'm going to sort of try to throw it all into the mix and try to figure this out. And then it's almost like they make it harder for themselves. And I know I've done that on standardized tests and things where it's like, I can't even make sense of anything that I'm doing now. Like, I'm just going to skip this or whatever. But so I wonder if in a research setting, you would sort of watch them develop this and try to get them to think through it. But in a teaching setting, if you saw these after, probably through homework or something like that, if you could sort of figure out certain remediations that you would take, and if you saw patterns across the kids, then you could isolate like, oh, that's because I used that one drawing. Or like, I had circles, but then I cut one of them. Like another way to do this would be to cut this pie into pieces, right? And so you have this drawing that's 4 circles with one of them cut into 4 pieces. And then when they get to this question, they sort of figure like, I got to do that for everything, and it sort of leads to.
Yeah, and I think like one of the sort of maybe reasons why this could be important is that confusion that the kid has where they're just sort of glomming things together and making things more complicated than they need to be is like, it's nearly invisible to the teacher.
Right.
We don't see a lot of evidence of that happening. So trying to figure out how to see it. Is
And without the inclusive or, it doesn't make sense. I think so. A lot of work we do with pre-service teachers is working with student work. We do this particularly on work samples where they're doing algorithms and they've notated things in like various buggy ways. But usually it's possible to deduce what the students, what procedure the student's doing, even though it's incorrect. But you look at the work and you think about it and you're like, oh, that's what they're doing. They're doing, they're doing this whole thing. They've got an algorithm that they're using and it's not the right one. With something like this, and that's a stance we advocate, right? So assume the kid's work makes sense. Try and figure out what it is. Use it as a way to understand what's going on. With something like this, though, it can really be like, what? There's no way. And without the possibility of like, oh, this could be something that kids do is they put things together. Right, so that's where this notion might be really helpful for teacher education, just as even a frame to look at this kind of work.
Though I wonder if you don't need some more process information to go along with it.
Probably. I think that'd be vital. I mean, your earlier question is so on point.
Just because you just don't know.
Yeah.
You might make one inference if they do all this at once and another. I mean, I can think of a bunch of possible inferences, but order would make a lot of difference. So if you had either video of the kids working or if you could collect it on kids drawing on an iPad or some way of recording.
Yeah, I was thinking of our pens with the microphones and stuff in them where you can watch how they're drawing and all that. Not that you need that if you're sitting there watching.
Yeah.
Since I have 3 minutes, the mechanism that the cognitive linguists are using to explain this is scalar implicature. But basically, if an adult hears the speech act like you can have pizza or ice cream, they're interpreting that as you can have pizza and not ice cream X, or you can have ice cream and not pizza. But with the inclusive interpretation of disjunction, it has an additional element of the meaning field, which is that you can have both. Right? So the kid's meaning field has an additional element. I was trying to explain again to my 4th grade teacher friend last night and decided to deprecate those slides to the to the very bottom, but you have to talk about it. Thanks.
Thank you.
There's some references.
Thanks for letting me join.
Oh, bye, Roman.
Bye.
Any questions?
Huh?
I'm not in the program right now. I'm actually a